So we're going to start a new chapter today, and at the beginning it's going to seem like we're not doing calculus. We're not going to be doing derivatives or integrals for a while, but we're going to be talking about infinite series and sequences, which is going to allow us, once we understand those pretty well, to do some pretty fun things using derivatives and integrals. So anyway, let's define an infinite sequence. An infinite sequence is basically just a function, but whose domain, instead of being a segment of the real number line, is going to be, whose domain is integers greater than or equal to some value of n. So all the integers greater than or equal to 5 or 3 or negative 10. But in general, n is either going to be 1 or 0. So how do you denote an infinite sequence? That's one way of doing it. Or you could make it look a little bit more like a function. So to give you an example, you could have 2 to the n. That would be an infinite sequence. Another way you could write that is a sub n equals 2 to the n. In both of these cases, to show what values of the integers you're using, it would be a good idea to show what the domain is. So in this case, you could say for n greater than or equal to 1. So another way besides this is that you could just start writing them out. So what are some of the values? When n is 1, you get 2. When n is 2, you get 4. When n is 3, you get 8. And then you could put some dots to say this keeps going. It would even be really nice if you put the general term in. So that would be an interesting way to show what that infinite sequence is. So, an infinite sequence, a sub n, we're going to be interesting. We're going to say it converges to L if and only if the limit as n approaches infinity of the nth term of the sequence equals L. If it doesn't do that, otherwise it diverges. So we're going to have an infinite sequence that either converges to a number or it diverges. Now, to actually show that a sequence a sub n converges to L, in order to prove that, we have to say for every epsilon greater than 0, there exists an n, a value of n, such that the magnitude of the difference between this nth term and L is less than whatever epsilon you picked for all values of n, little n, greater than this big N. And just like when we first did limits with functions, this was the real formal definition of a limit existing and a limit to equal a value. It's kind of a complicated one, and just like with functions, we're not going to end up using it a lot. But I'll show you why it's so nice to have that. So let's just take a fairly simple example and show how we could use this definition to show that a sequence converges. So say you had the sequence 1 over n. That sequence, we're going to try to prove that it converges to 0. In order to do that, we have to say for every epsilon greater than 0, there exists a value of n such that the nth term minus the limit, the difference between that nth term and the limit has to be less than whatever epsilon you can pick for all values of n greater than the n that we get to pick. Well, algebra-wise, since n are positive numbers, we can drop the absolute value sign, and we just have to say that 1 over n is less than epsilon for the n that we pick. Well, knowing our inequality rules, if we flip everything upside down, we have to change the inequality sign. So now I just have to show that n is greater than 1 over epsilon for all n greater than this big number n. Well, how could I prove that? All I'd have to do is pick my big N to be 1 over epsilon. And then I would have proved it. For n greater than 1 over epsilon is going to be true for all n greater than 1 over epsilon. Now, that might seem a little obscure, so let's just say there's an example where somebody picked epsilon to be 0.001. So if you picked epsilon to be 0.001, they're challenging us. Can we get a term of our sequence to be within 1/1000th of 0 for all values in the sequence past a certain point? Well, if this is true, what would I pick n to be? 1 over 1/1000th or 1,000. So as long as I go past the 1,000th term in the sequence, I'm showing that all my values are within less than 0.001 of the actual limit. And what would that sequence look like? It'd be 1, a half, a third, 1,000th. So that's what that infinite sequence would look like. And you can see once you get past this point right here, all the terms are less than 1/1000th away from our limit of 0. You're probably thinking right now, I'm glad that I'm not going to have to do this every time. But what this is really good for is the math gods were able to use this theorem to prove all the rules like they did for limits of functions. In other words, that if you have two different, say you have two different sequences, a sub n and b sub n. If you wanted to look at the sequence a sub n times b sub n, we could just see what this one converged to and what this one converged to, and then this is going to converge to this. Say this converges to L1 and this converges to L2. We know that that's going to converge to L1 times L2. We don't need a special product rule. So limits are going to be our friends in sequences as well as they were in functions. So in general, we're not going to have to go through this anymore to prove that this converges. We can just take the limit as n approaches infinity the same way we did it with functions. We can eliminate everything but the highest power of n, and we see the answer is just 2. That was easier than putting this expression in place of 1 over n and putting a 2 right here and going through all that algebra. So thank you to the math gods for allowing us to find the limits of infinite sequences in a much easier way. Okay, so let's just take a look at this infinite sequence for a minute. Do you think that that converges? And if so, what does it converge to? Well, one thing, this minus 1 to the nth power. Let's look at this if n is even. If n is even, negative 1 to the nth power is just 1. So the sequence just becomes n plus 1 over n. So if we took the limit as n approaches infinity, let's just call this a sub n, what are we going to get? We're going to get the limit as n approaches infinity of n plus 1 over n. Looking at the highest powers, we know that's going to just be 1. But if n is odd, then it's going to be the same as this, but there's going to be a negative sign in front. So then the limit as n approaches infinity of a sub n is going to be negative 1. So we can see that if we were writing out this sequence, it's not going to be converging to a number. It's not going to go off to infinity, but it's not going to be going to a number. So if you even started to write some of the terms, when n is 1, you get negative 2. When n is 2, it becomes positive, and you get 3/2. Then when n is 3, it's back to negative, and you get 4/3. You can see that these numbers are getting closer and closer to 1 in absolute value, but they're not converging to either 1 or negative 1. They keep flipping back and forth. So you would say that that sequence diverges. Even though it doesn't go to infinity, it doesn't for sure go to a number, so you'd say it diverges. So there's 2 ways that infinite sequences can not converge. They diverge. One is if they go to infinity. Another if they don't end up going to any single number, as in this case. Okay, so let's take a more complicated infinite sequence. So say the sequence was 4n plus 1 over n with a square root in it, like that. What we have to do to find out if that converges is to take this limit as n approaches infinity. Now the question is, as complicated as that is, can I look at just part of it? Can I just look at the limit of the inside part and then take the square root of it? Well, this is again where we're thankful that we have this more complicated definition of convergence, and we're thankful to the math gods for having proved this. What they proved is, if the sequence a sub n converges to some number L, and if a function f of x is continuous at x equals L, then the sequence f of a sub n converges to f of L. Now, you might have to read that a couple times to really have it sink in, but what it's really saying is, I've got a function here, f of x equals the square root of x, which is continuous for all real numbers greater than 0, greater than or equal to 0. So I can just look at this inside part, and I can see that that converges to 4. And I know that f of x is continuous if x equals 4. Therefore, I can say this whole sequence converges to the square root of 4, or 2. I don't have to think of it all at one. And the same thing here. This is a really complicated looking sequence. But if I just look at the inside part right there, what's the limit of this as n approaches infinity? Well, we can ignore the 3 and the 1, and n squared has coefficients pi and negative 4. So that means this inside part converges to negative pi over 4. And the tangent is continuous at that part of the curve. So we know that this whole thing converges to the tangent of negative pi over 4, which if you know your automatics is going to be negative 1. And one more, just in a slightly different form. Instead of asking for the limit, I'm saying, does this converge? Or does it diverge? Well, we can just look at 3n over n plus 1. The limit as n approaches infinity of this is 3. And we know that the function e to the x is continuous at x equals 3. So this whole thing doesn't diverge. It converges to e cubed. So let's get to another one here. Now, as n approaches infinity, you have the natural log of n over the square root of n. So we're looking at, again, the sequence. We want to know, what does that converge to? Or does it diverge? So we're taking the limit. But this isn't quite as easy. Both the natural log of infinity and the square root of infinity are both going to infinity. So we can't really easily come up with an answer. But luckily, we have one more theorem that was proven. And that is, if you have a sequence a sub n, and you have a function y equals f of x, such that f of n equals a sub n. Then, if the limit as n approaches infinity of a sub n equals L, then the limit as n approaches infinity, as x approaches infinity of f of x equals L. Basically, what it's allowing you to do, this theorem, is you can change an infinite sequence into an infinite function. So we can say the answer to this is the same as the limit as x approaches infinity of the natural log of x over the square root of x. And here, we still have the same problem of infinity over infinity, but now we can yell l'hôpital. And we can say it's equal to the limit as x approaches infinity. And now we take the derivative of the numerator and the derivative of the denominator, and that denominator becomes 1 over 2 root x. So So when we take 1 over x and we divide it by this, we end up with the limit as x approaches infinity of 2 over root x. And as x approaches infinity, that's going to approach infinity. So the whole fraction is going to approach 0. So I can go back and say the answer to that must be 0. Basically what it's saying is you can use L'Hopital on sequences also, which is really nice. Okay, now, there's another kind of sequence that we should probably talk about if we're talking about sequences. So, say we have this one. Let's, instead of calling it a sub n, call it f sub n, just for a change of pace. And say this sequence is defined like this. F of 1 equals 1, f of 2 equals 1, and then f of n plus 1 equals f of n plus f of n minus 1. Let's see what that sequence would look like. F of 1 equals 1. F of 2 equals 1. Now, what's f of 3? F of 3 is going to be f of 2 plus f of 1. So 1 plus 1 is 2. F of 4 is going to be f of 3 plus f of 2. So you get 3. Then we're going to get what? 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. And we get a very famous sequence, which a lot of you probably have heard of, the Fibonacci sequence, which has a lot of really interesting things. If you take the ratio 2 over 1, 3 over 2, 5 over 3, 8 over 5, 13 over 8, if you keep taking those ratios, they get very, very close to a really important ratio called the golden ratio. And there's so many things you can read about that. Architecture has been done in ancient times. The Greeks used it to build things. Paintings have been done using the golden ratio, and it shows up in nature. So this is a real interesting sequence. But this is called a recursive sequence, because you can't get to the 1,000th term just by plugging something in. Like right here, you could get to the 1,000th term of that sequence just by plugging in 1,000. Here you have to go through this whole process. To get to this value, you have to know what came before it. So this is called a recursive sequence. So let's just end this up. No proofs, just kind of fun. Take this sequence here, x to the 1 over n. As n approaches infinity, so x could be like any number greater than 0. Could be like 5 or 10, 100. What happens as n approaches infinity? That is going to approach 0. Well, we know anything to the 0 power is equal to 1, but what if you put in like a trillion? Well, it can be proven that it doesn't matter how big of the number you pick. If you let n approach infinity, that's going to take over, and you're still going to get 1. Again, I'm not proving these. I'm just kind of showing why it makes some sense. And then, if you go to your calculator and take like x to be 100, and then you let n approach infinity. So I'm not going to make it go all the way to infinity, but if I take it to the 1/10,000th power, I get 1.0004. So if I put 10,000 in for n, I don't have to even get to infinity, and you can see how close it's already getting to be 1. And this is just a little bit of an extension of this. Not only if you pick a number, but what if you let n approach infinity? So this is getting like to a millionth power of a million. It still turns out to be 1. So this 1 over n power, as that gets close to 0, really takes over everything else. So even if I take a million to the 1/millionth power, you get really close to 1. Now, what about if x is not a whole number? What if it's less than 1 in absolute value, like 0.5 or negative 0.6? Then, as n approaches infinity, if you take a fraction and take it to a really high power, what is it going to tend to approach? Well, 1/2 times 1/2 is 1/4. Times 1/2 again is 1/8. But what about if you come really close to 1, like 0.99? Is it still going to do that? Well, I did. 0.99 to the 100th power. Because 0.99 was almost 1, it doesn't go to 0 quite as quickly. But if I take the 1,000th power, you can see that it is approaching 0. So that means if you take any fraction to what approaches an infinite power, you're still going to get to be 0. And we did something very similar to this when we did functions, except I had a 1 here. You might remember, I proved the limit as x approaches infinity of 1 plus 1 over x to the x power. I proved that to equal e. And it can be proven that 1 plus x over n to the nth power equals e to the x. So this is just a stronger form of this, and it shows that it works in sequences as well as with functions. So for instance, if I just put -3 in here for x, it should go to e to the -3 power. Well, just on a calculator, if you take 1 plus -3 over 1,000 to the 1,000th power, you get 0.0496. E to the -3 is 0.0498. That's not a proof, but a very good indication that this is also true. So I really have kind of proved this one. These three take quite a bit of proof, but if you want to look them up, they can. They're going to be like this one where you have to use logs. You have to let y equals this and take the limit of what the log of that goes to, and then we can prove what the actual sequence goes to. Anyway, I think you're probably, if you just kind of in your head get an idea what those would go to, they would make some sense to you. So anyway, that kind of finishes up infinite sequences. Tomorrow, we'll get why we really learn about infinite sequences as we'll get into infinite series. So until then, take care.